I put in new batteries, should be fine. And now we have rechargeable batteries for the microphone. All right. As a quick follow-up to what we did yesterday about kids stealing candy bars as opposed to bases stealing protons. Recognize there's one major difference between these considerations, which I will admit I had not thought about myself until about a year ago. And I recognized the flaw in my logic. The flaw is, as bad kids steal candy bars, they're still bad kids. But as Bronsted bases steal protons, are they still Bronsted bases after they've stolen the protons? No, now they're the conjugate acids. Which means in a solution, as Bronsted bases steal protons, what happens to the original quantity of Bronsted base in the system? Decreases. Now, from a material balance standpoint, there's no decrease. But regarding the actual bases which are in the system, that gets smaller because the bases are getting protonated. So I'll ask you to think about these considerations. For a hypothetical acid 8Z, which we stated as a given, that had a Ka value of 18. We really didn't give that, we calculated it. Because at 1.0 molar initial molarity, we said, let's imagine that K8, that 8Z ionized 95%. And so with that, we showed how we could get Ka for 8Z. Showed it was 18, a big number, but still smaller than Ka for hydronium ion, which means since we define acids, strong acids, pardon me, as hydronium ion or any acid stronger than hydronium ion, which means any acid with a Ka value bigger than 55.5, 8Z is now argued to be a weak acid. Strong as far as weak acids are concerned, but categorically still a weak acid. So let's imagine making a system. 54 moles of water, 1 mole Z minus, essentially a 1 liter volume system. Now, how would we put the 1 mole of Z minus in the solution? What would we do? We can't add Z minus by itself. You can't go to the side shelf and buy a bottle of negative ions or ions which only have one charge type. Cations or anions only. Can't do that. What are you going to do to put Z minus in solution? What would you do to put chloride ion in solution? Add a soluble solid chloride ion, like sodium chloride. So, take sodium Z minus, sodium zide, or potassium zide, whatever it is. Dissolve it. You'll have the mole of Z minus. Now, with this system, we're going to bubble in a mole of HCl gas. What do we know about HCl gas? Strong acid, isn't it? So strong that it has the capacity to react with water to an extent of 100%. And after having found that Ka8Z is 18, what do we know about the base strength of Z minus compared to the base strength of water? Which is a stronger base? Z minus or water? Don't forget conjugate theory. If we have discovered with our arithmetic that we did yesterday that if we were to insert HZ into our acid base table, it would be underneath hydronium ion. Well, that guarantees that in the base column, Z minus would be underneath water. How do the bases change relative strength-wise? They get stronger which way?
Down.
Right. Z minus has got to be a stronger base than water. If the conjugate acid of Z minus is a weaker acid than the conjugate acid of water. This is what conjugate theory tells us. That's the way the acid-base table which we have is constructed. Any acid-base table is constructed in this fashion. Okay? So we're going to bubble in HCl. We know the HCl will be used entirely. Will all the protons from HCl in this system be captured by Z minus, because Z minus is a stronger base than water? When we make this system, will all the H pluses supplied by HCl be captured by Z minus and convert to HZ? Is that true? I'm asking, is that true?
Yeah.
Well, if that were true, we would wind up making 1.0 molar 8Z solution, wouldn't we? If this is a 1 liter volume. But we said at 1.0 liter, in 1.0 liters of 1.0 molar 8Z, how much was HZ ionized? 95%! We did this yesterday, right? So I repeat the question. When I bubble in this 1.0 moles of HCl, will all the protons from the HCl molecules be captured by Z minus? Heck no! Why not? It's a stronger base than water. Don't forget the gang-up factor. What's the gang-up factor? All right, let's ask this question. Now, some of you heard this story before. I'm not much for prize fighting, but I admired a fellow whose name was originally Cassius Clay. He changed it to Muhammad Ali. Anybody remember this guy? Muhammad Ali. Anybody have a recollection of how good a fighter he was when he was in his prime? He was the best. He was really good. Tell me, if any one of us got in the ring with Muhammad Ali when he was in his prime, how long would we last? Not very long, would we? But if the whole daggone bunch of us jump in there, we could gang up on him, couldn't we? Now maybe 25 of us would get murdered along the way, but eventually we'd overcome him. And that's what's going on in this system. Yes, Z minus is a stronger base than water, but water grossly outnumbers Z minus in this system. See the initial ratio? 54 moles water, 1 mole Z minus. And after we talked further about the fact that if Z minus got all the H pluses, you'd wind up with 1.0 liters of 1.0 molar HZ, in which the ionization extent of HZ would be 0. But we knew it's 95%. Which guarantees that water's getting an abundance of H pluses. In fact, in this system, after H plus grabbing is done, keeping in mind that when water grabs H plus, you get hydronium ion. And when Z minus grabs H plus, you get HZ. Which base gobbled up most of the protons in this system? Water or Z minus? Most of the protons. You remember this? We started with 1.0 molar HZ, didn't we? And we were just creating the same system, only starting in a different way. And after the HZ went to an ionization extent of how much? 95%. How much of it was left? Remember this? At equilibrium, that's all that was left? Yeah, that's all that was left. But at equilibrium, we had this much of this stuff, didn't we? So who got most of the protons in this proton fight? The water molecules by far. Hey, 0.95 to 0.05. That's what you get when water grabs H+. That's what you get when Z- grabs H+. 0.95 to 0.05, that's 19 to 1. So because of the gang-up factor, even though Z- is a better base than water, water got most of the protons in this fight. Keep stuff like this in mind. So I'm going to ask you two questions. What happens to this as equilibrium is established? You can answer this question by what you see on the board. Now let's ask it in a different fashion. For the same system, but with different strengths. If water is a stronger Bronsted-Lowry base than Z-, what would happen to this? Are you following the questions? You think about the questions. Now we'll proceed. And we'll talk about these questions further when necessary. Back to practicalities. We talked about this when we started this conversation on analysis of Bronsted-Lowry acid-base equilibrium systems. How do we get Ka values? I've heard wise students in the past say, well, you look them up in a book. Someplace along the line, there was no book in which to look up this information. Somebody had to make some measurements. So if, for example, we imagine acetic acid is an acid whose Ka value is not known, just like what you folks did in laboratory this week, wouldn't you say? That's what you did in laboratory this week. You did an experiment which imagined that Ka for HAC was not known. And you did work which would allow you to get a reasonable estimate of KaHAC. You make a solution of HAC for which the initial molarity is known reliably. Let's imagine we make one of 3 sig figs. What you made in the laboratory was just 1 sig fig. 0.300 molar HAC. Okay? That only means you got water as the solvent, you measure 0.300 moles of HAC after you do the appropriate formula mass arithmetic. And then you dissolve this in sufficient water until the total system volume is 1 liter. There's your 0.300 molar HAC, and in that case you'd have a liter of solution. You measure the pH. You get 2.63. You can get 2 significant figure pH reliability with the pH meters you have for use in laboratory. So you now know for this equilibrium system that the hydronium ion molarity is 2.3 times 10 to the minus 3, and as is the acetate ion molarity, 2.3 times 10 to the minus 3. Where do these values come from? This is an arithmetic question. They come from the pH. As we told you folks, this is arithmetic which you need to know how to do. But if you need assistance, we'll be glad to help you on a one-on-one basis. You assume the responsibility of asking for the assistance if you need it. All right? So here's the Ka expression, chemical version for HAC. Hydronium ion acetate ion molarities are equal, as the stoichiometry of this reaction dictates. So we got up top 2.3 times 10 to the minus 3 quantity squared. What's the equilibrium molarity of HAC? Well, you got to take the molarity with which we began. Apply material balance considerations, which we talked about yesterday. Recognize that as acetic acid reacted, it will convert to acetate ion. So, the initial molarity of acetic acid less the amount of acetic acid which disappeared. That's this. That gives the equilibrium molarity of acetic acid. Here it is. Now, when I do this subtraction, What do I get? 0.30 less 0.0023. I've just written the scientific notation value as a decimal fraction. This number is the same as this number. When I take this number and subtract from it this number, what do I get?
2987.
I get 0.2. What?
987.
Can't go to 4 sig figs. The molarity of acetic acid is only known to 3. So what do I get? 0.298. So I take this product divided by 0.298 and I get Ka for acetic acid. And I'll get 1.8 times 10 to the minus 5, just like you see in our acid-base table. I've looked up Ka value for acetic acid in a whole bunch of different tables. It seems as if this is the accepted value. I've not found any tables that give a different Ka value for acetic acid Ka at normal lab conditions. Now from this, we get an important generalization. This stuff is all in the notes, but since it's important, I want to take some time to talk about it. If we have a solution prepared by dissolving one and only one ionizing solute, like acetic acid, or ammonia, or any other number of weak acids or bases which we could consider from our acid-base table. As it follows from this analysis, the equilibrium established with the ionizing solute, either the acid or the base, will create, for the acid, hydronium ion, and the conjugate base of the acid. For the base, it'd create hydroxide ion and the conjugate acid of the base, at equal molarities. So let's represent the molarities of these species, with the molarities being equal as X. This is because it's the most common representative of quote-unquote unknowns that we see in algebra class. So the Ka becomes X squared divided by the equilibrium molarity of the ionizing solute. Well, we've shown how to get the equilibrium molarity of the ionizing solute. You take the numerical label on the bottle, the M sub I value, the initial molarity, and subtract from it the molarity of a derived species, acetate ion derived from acetic acid. And you get this. Same idea for a base. Now, what can we do with this generalization? Let's take a look. Well, we can do that. That's okay. For starters, if you were in the laboratory pursuing this, based on the information we have on the board, what do you think is a likely way by which you would obtain this stuff? Of making this available to you. That's on the reagent shelf in the laboratory. So if you have that available, what would you do to that to get this? Diluted by what ratio? Solvent to parent solution. What's the ratio? What's the ratio?
3 to 1.
What is it?
3 to 1.
I heard a ratio of 3 to 1. What is that?
1 to 10.
1 to 10. Well, let's imagine that I have, as I said, this available. And I choose to measure 500 milliliters of this solution. How do I turn all of this into that? You've been doing dilutions. Throughout 46L, you're going to have to do dilutions all the time.
Add a liter of water.
You sure that's going to work?
3 moles to
Moles? What would you do? You're going to run to the TA and say, I don't know how to do this, help me? If you do that and I'm the TA, I'm going to say, too bad. It's your job. This is a really big graduated cylinder. Well, unfortunately, if we don't move out of here, they're going to come and raise hell. So go out of here. There's a door right over here. Go that way. Stay close as you can, so that when this mess stops, we can get back together. And plug your